So good morning, guys. Today we're going to be doing our initial dive into heat transfer. Today's going to serve as an introduction to heat transfer and an overview, with Thursday looking more in depth in conduction. We spend a good bit of time in conduction. We spend some time, quite a bit of time actually, on convection as it applies most applicably to heat exchangers and heat transfer equipment. And if we have time, we'll get into radiation, but it's the application and understanding of radiative heat transfer, feels more like physics than chemical engineering. And so it's traditionally not been really explored to a great extent in this class. But if it's something that interests you all, as well as if we have sufficient time at the end of our discussions with heat transfer equipment, we may explore and get into it. So with that, I'll kick it over to our notes application, and we'll go ahead and get started. So today we're looking at an overview or an introduction to heat transfer. I need to figure out why it defaults to red. And as always, if I start to go really fast, or if you need me to zoom out or make any changes, please let me know. So we can't do an exploration of heat transfer until we can effectively identify and describe what is heat. So the first person on my list is Eduardo. Can you give me an idea of what is heat?
It's energy transfer
All
through
right.
a like a heat gradient.
That's close. That's really close. I appreciate it. So heat is an energy transfer due to a temperature gradient, right? In other words, we consider this the driving force for heat transfer. So we can't have heat or heat transfer without the existence of a driving force. And so one thing I like to state is that when it comes to heat transfer,
There you go.
we are interested in the rate of heat transfer. And we can discern this from what we think about in terms of thermo. Where we are concerned the amount of heat. And so in your mechanical energy balance, you'll solve for what's typically referred to as Q, which is the variable used for heat. In this class, we're more concerned with the rate of heat, or Q dot. One other thing that we can be concerned about is, in addition to the rate, the heat flux. Say in a given system. which I typically designate as a lowercase q, which is simply the heat transfer rate over the heat transfer area. And it's important to consider the heat flux because identification of heat flux allows design system, what I consider, I'll say process design considerations. For example, if I want to size a heat exchanger, I have to have some sort of information, not necessarily about the total heat Q, but the actual expected heat flux in our system, or lowercase q dot. So is everyone following along okay? Am I moving too fast, or are you all comfortable with this pace?
This pace is fine, Dr. Lopez.
Perfect, thank you for the feedback. So, with this in mind, there are three forms of heat transfer. We have conduction, convection, and radiation. Now, conduction is designated as heat transfer by direct contact, where we have high energy molecules or particles transferring energy to low energy molecules. Convection is heat transfer that occurs by fluid flow. And it's also considered an enhancement of heat transfer over conduction due to fluid flow, which we'll talk about more here in a second. And lastly, we have radiation, which is heat transfer through emission of electromagnetic radiation, which fun stuff. The calculations can get quite complicated, but it's always fun to kind of look at. So these are the three forms. When it comes to what we discuss most often and as it applies in process engineering, conduction and definitely convection dominate. However, we also do have to consider areas where radiation can come into play. And so the best way to kind of visualize these three forms of heat transfer is in this slide showing here, where we've got essentially a pot of water that's boiling, where we can see convection occurring within the water itself, and that the energy is being distributed throughout the water in the pot through natural convection currents that occur. And so we consider that what's known as natural convection, and that fluid flows as a result of the temperature gradients that exist. We can consider conduction if when the handle gets hot, if we're fool enough to touch it without a pot holder, it hurts. And we have, that heat transfer that happens with direct contact with the handle. And then we also have radiative heat transfer through emission of electromagnetic radiation by the fire outward. If we ever sit in front of a campfire, you feel the warmth due to the electromagnetic radiation that's emitted, particularly in the infrared region. And so this is a really good example that we can see of above all conduction, convection, and radiation. So what we're going to do today is take little glimpses at each three of these forms of heat transfer and discuss the primary equations that we can use to determine heat transfer from each of these mechanisms, starting with conduction. So conduction, as I said, is heat transfer due to direct contact, and it's governed, or I could say governed by what's known as Fourier's law of conduction. And Fourier's law states that the heat flux through an object is equal to the driving force or potential gradient, or excuse me, temperature gradient that exists in the object multiplied by a constant of proportionality. So if I have, let's say, an object, and I have T1, T2, and T1 is greater than T2, I can expect some heat transfer to occur, and that heat transfer will equal to that proportionality constant, something I take a big Q, the area where heat transfer is occurring, keeping in mind this is now surface area as opposed to what we dealt with a lot of in fluid being cross-sectional area. Heat transfer exists along surfaces, and then we have to consider the temperature gradient, where if we're considering things outside of the differential, and if we integrate between two temperatures among a particular thickness, we can also describe this by the equation here, where I see Q is equal to negative K times the surface area times the temperature gradient delta T over the thickness of interest, or delta X. So in this case, this would be delta X. And so definitely keep this equation in mind, actually both of these, because they will become extremely important as we consider calculations and heat transfer via conduction. So then the question then becomes, what is our constant of proportionality? Well, K is simply the thermal conductivity of our material. And the thermal conductivity is the measure of a material's ability to conduct heat. An important thing to consider about thermal conductivity is that thermal conductivity, it is at what's known as an intrinsic property. So it's unique to each material. And so what I
Dr.
like to,
Lopez, I have a question really quick.
yes.
What's the difference between intrinsic properties and intensive properties? Are they just synonyms for the same thing?
Did you say intensive properties?
Yes, I did.
I haven't heard the use of intensive properties. I would guess that they're being used in the same way.
Okay.
Yeah, a quick Google search. Yeah, I'm guessing it's kind of synonyms. Intrinsic, extrinsic. And so it's important when it comes to thermal conductivity that for a given material, what this means is you can look it up. Thanks, Google. And so, for my next interactive question, Harrison, what type of materials do you think exhibit high thermal conductivity values? And we can expect to have a high ability to conduct heat.
So metals is the first type of material that comes to mind.
Metals is correct. So what we can say is in general, right, there's always exception to the rule, but in general, metals have high values of thermal conductivity. Nonmetals have moderate to low values of thermal conductivity. And also, since we're considering direct contact, the thermal conductivity of a solid will on average be greater than the thermal conductivity of a liquid, which will on average be greater than the thermal conductivity of a gas. And one other thing I like to point when it comes to thermal conductivity, the units in SI are watts per meter Kelvin or watts per meter degree Celsius. It really doesn't matter. And in English units, the units are in BTUs per hour, feet, degree Fahrenheit. So keep that in mind when it comes to these systems. All right, the next question I always like to ask is, which metal?
Could you scroll back up to those
Here, I'll zoom out. How's that?
things for a second?
Of course.
Thank you.
Which metal has the highest thermal conductivity? All right, so Kamisha, do you want to take a guess? Highest thermal conductivity.
I probably would say like maybe stainless steel.
Stainless steel is actually surprisingly lower than you would think. It's even lower than, cast iron. That's a good guess. Anybody want to help her out?
Maybe copper.
Copper is a really good guess. It is the second highest, right? That's why when we consider the fact that most electronics, to some degree, utilize copper.
Would it be aluminum?
It would not be aluminum.
I
So
would
let's see.
guess silver.
Silver.
Copper is the highest, second highest. But you are correct in that silver is the highest. And to the credit, Copper's a very, very close second. If we see here in the slides I've prepared, you can see a list of metals and their thermal conductivity. So just looking at 25 degrees Celsius, we can see copper has a thermal conductivity of approximately 401 watts per meter Kelvin, and silver ekes out of it just a little bit at 420. Now, copper is used in electronics a lot more just because primarily copper has traditionally been cheaper than silver. It's more readily available. However, when it comes to high-end electronics, you will still see silver used in certain applications. If anyone here is into, PC building, that's why you use what's known as silver paste when attaching computer chips to heat sinks. Another thing that you see in a lot of electronics is gold. Why do we think gold's a pretty good use, even though it's the third highest? And let's see who's next. Juliana, what do you think? Why would we want to consider even using gold, even though its thermal conductivity isn't as high as some other metals?
Wow. Wait, what was the question?
The question was based off a comment that I said that we also can find gold in a lot of electronics, even though its thermal conductivity, which is also related to electrical conductivity, isn't as high as some other metals. So why might it be advantageous to use gold in electronics?
Is it, I don't know, is it more dense?
No, that's a good guess. It's typically because, I got a chat. Gold means money. Well, yeah, they can charge more. I like that, Eduardo. Now, gold is advantageous in electronics and primarily because gold has an extremely high corrosive resistance. And so it can outlast a lot of these metals, particularly gold and silver. Copper oxidizes fairly easy. So when placed in the wrong environment, copper suffers very quickly. And so you can essentially get a shell of copper oxide that exists on the outside of your metal, rendering it useless. Silver has similar issues, though it's slightly better in terms of resistance than copper, but gold definitely outshines in terms of durability and corrosive resistance. Now there's only one other material that I can point to that has even higher thermal conductivity than copper and silver. And so the material with the highest outright.
Dr. Lopez, can you switch screen?
Yes, I can. Which you may or may not be able to guess. But surprisingly, it is diamond, whose thermal conductivity is approximately 2.2 kilowatts per meter Kelvin, or 2200 watts per meter Kelvin. Though, as you can imagine, as expensive as gold is, diamond's quite a bit higher. And so, unless you really want to go for broke, you're really not going to be using diamond in a whole lot of applications. But fun thoughts and consideration when it comes to thermal conductivity as it applies to heat transfer, as well as the other considerations when it comes to material selection.
Why is it that diamond is the best?
Why is it that diamond is the best? I don't think I can give you a definitive answer. I would probably have to attribute it to its highly ordered structure and it comes to its molecular arrangement. Because if what do we could, because diamond is nothing but carbon. And when carbon's in a very pure state, it has excellent thermal and electrical properties. And you can even argue, if I looked it up, graphene would probably be somewhere on the order of diamond when it comes to thermal conductivity. Yeah, doing a quick Google search, I even find graphene, which is just an atomic layer of carbon. The thermal conductivity of graphene can vary anywhere between 3 and 5 kilowatts per meter Kelvin, or 3,000 to 5,000 watts per meter Kelvin. However, as always, the issue with graphene is stability. And if you can't make a material that can be stable as environments fluctuate and processes have perturbations, even though you might have outstanding properties, the applications are going to be limited. So I'll say the materials. So jumping back to our application with heat transfer, what we can see here in this slide briefly is what we find in terms of thermal conductivity of nonmetals, where we have water, which is fairly low as compared to the metals, at 0.7 to 0.5. Then we have various gases, extremely low, several orders of magnitude below what we've been looking at. And so, like I said, what we find is that liquids have lower thermal conductivities than solids, and that gases typically have even lower thermal conductivity. And this difference is exhibited on the orders of 1 or 2 orders of magnitude. So with that, let's take a look at an example of doing calculations for heat transfer, assuming conductive heat transfer is the only thing that's occurring. So in this example, I have a single pane window, half an inch thick, with a surface area of approximately 0.4 feet squared. Is used to I separate a home, the inside from the outside, with the inside being 75 degrees Fahrenheit and the outside being approximately 38 degrees Fahrenheit. The question asks, what is the heat transfer rate through the window if the thermal conductivity of that glass is approximately 0.6 BTUs per hour per foot per degree Fahrenheit? And so let's take a look at this first step. We'll calculate the heat transfer, then we'll look at the second half of this problem. So in this example, we have a window where the inside is 75 degrees, the temperature on the outside is 38 degrees. The thickness of the window is half an inch, or 0.04167 feet. And the thermal conductivity as provided is 0.6 BTUs per hour foot degree Fahrenheit. So if I want to consider the heat transfer by conduction, I need Fourier's law, which states Q is equal to K, A sub S, delta T over delta X, which equals 0.6 BTUs per hour degree Fahrenheit feet times the surface area, which was provided as 0.4 feet squared, times the temperature gradient, or 75 minus 38 degrees Fahrenheit, divided by the thickness of the window, which was a half an inch, or approximately 0.04167 feet. looking at the system, I can do a quick unit check and say, okay, I have 2 feet on the bottom, cancels out my feet squared on top. I have a degree Fahrenheit on top, it cancels out my degree Fahrenheit. So in English units, my heat transfer rate should be given in BTUs per hour. And that comes to approximately 213 BTUs per hour. So any questions on that example problem? Do you guys kind of see how I was able to apply Fourier's law based on the information given? I assume by your silence that you are all stunned and you are feeling comfortable with Fourier's law. So let's look at the second half of this problem. As it states, if the home is going to be heated by natural gas, which costs approximately $1.50 per CCF. CCF is essentially 100 cubic feet. That's just the way it's written. And if 1 CCF of natural gas outputs 1 therm, which is approximately 100,000 BTUs, this is an actual unit, what is the cost of the energy loss through the window in a month? So the second half asks us to estimate the energy cost associated with the heat loss through the window during that month of December. So, as it stated, put a little box here. So it said natural gas costs approximately $1.50 per CCF. 1 CCF outputs approximately 1 therm. And 1 therm is approximately defined as 100,000 BTUs of energy. And since it's December, I'm going to assume 31 days in a month. So if I want to calculate the cost of the energy lost, I can say, well, I have 213 BTUs per hour leaving through the window due to heat transfer. Then I have 24 hours in 1 day. I have 31 days in my month. And then I have approximately 100,000 BTUs in 1 therm. And 1 therm comes from a CCF. And a CCF costs approximately $1.50. Doing a unit conversion check, hours go away, days go away, months do not. BTUs go away, therms go away, CCF go away, and I'm left with dollars per month. So if I do that calculation, what I find is the energy cost due to that heat loss is approximately $230 per month. Any questions on that example?
Yeah, Dr. Lopez, you said $230 per month, but you wrote $2.30.
I'm sorry, $2.30.
Okay.
My brain and my hand argue a lot. I'll think something and I'll say another, and then my hand will write a third thing. It happens. Any other questions? All right, if not, let's shift gears then and talk a little bit about heat transfer by convection. Now, as stated earlier, convection is heat transfer due to fluid flow. And it's generally expressed or defined by what's known as Newton's law of cooling. And Newton's law of cooling simply states when it comes to convective heat transfer, we have the heat flux by convection is simply the temperature gradient, dT, times another constant, or shouldn't constant of proportionality, but a corrective factor of proportionality. Now, one thing that differs is we don't see the delta x, we don't have the gradient through an object, because when it comes to heat transfer, convection only happens along surfaces. And so if I express this in a more generalized form, I can say Q is equal to H times known as what's T sub S minus a T infinity, where T sub S is my surface temperature, T sub infinity is my surrounding or ambient temperature, and my H is known as my heat transfer coefficient. And once again, for illustrative purposes, if I consider it not as a flux, but as a true heat transfer, I would write it as H times the surface area times T sub S minus T infinity. And once again, I'll give you all my wonderful circles of important things that you should probably write down and put in a book that's necessary for exams, midterms, and just life in general. Now, let's talk a little bit about everybody's favorite variable in this class, H, which is our heat transfer coefficient. Now, the key thing when it comes to heat transfer coefficient is that this is an extrinsic property, meaning not only is it dependent upon the materials involved, it also is dependent on the geometry and the flow conditions and everything that can happen in a given system. So it's important to know. You can Google and look up K. You unfortunately cannot do that for our heat transfer coefficient, H. I also like to consider this. This is the Waldo of heat transfer. Especially as it applies to this class, because what we'll find when we start looking at heat transfer equipment, 80% of the work is finding your heat transfer coefficients. Because there's so many things that are involved in identifying it that you have to consider. It's the Waldo, and that's who you got to find. So with that in mind, let's do some thought experiment. I shouldn't say what. So how can we typically maximize our heat transfer by convection? So what do you think? So today, next, I'm going to call James. Well, how do you think we can maximize heat transfer by conduction? What are some things we can do?
Conduction or convection?
Convection.
Can you manipulate the temperatures?
You can. We can increase our temperature gradient. Do you have any other ideas?
Maybe increase the surface area?
That's something. You got one more for me? Or is that all you got?
That's about all I got.
All right, that's fine. Let's see if I can find somebody to help you out. Cameron, do you have any other ideas for us on how we can increase and maximize heat transfer by convection, excuse me.
I know we want to increase our H, so it kind of depends on how we calculate that.
Well, without being told how to increase H, what things would you guess may increase it, as well as increase heat transfer?
It's dependent on fluid velocity, so increase of fluid velocity.
That's correct. We can increase our fluid velocity. Very good. There's a couple other things, but I think that's enough for now. Thanks, Cameron. So, a lot of what we'll get into in this class will be how is H defined and how can we identify it based off of the type of flow, hint, hint, that we have in our system. But for now, let's look at an example. If I can find the right slide. So in this example, we have a 2-meter wire with a 10-centimeter diameter extending across a room at 20 degrees Celsius. And I'll say heat is being generated in this wire due to an electrical current which is passing through it. If the surface temperature of the wire is measured to be 150 degrees Celsius, determine the heat transfer coefficient between the wire and the air, assuming the voltage and the current in the wire are found to be 110 volts and 0.5 amps. So I will give you guys a second to write this down. All right. So for this problem, what I'm going to do is I'm going to shoot you off to breakout rooms, but as everybody yesterday had issues with this problem a little bit, what I can tell you, which I didn't tell them, is that you can calculate the power in the wire as a product of the voltage and the current. This gives you power in watts. And in this problem, I'm assuming all of that power is being transferred as heat. So this is your heat transfer rate. So there's your hint. Now I'm going to shoot you all into the nether. And I'll give you a few minutes to work together to do this problem. How's it going?
So
Okay,
we're
so
trying to
far.
find the heat transfer coefficient, correct?
Yes. Are you guys having any issues?
It should be straightforward once you gave the hint. It's just the power divided by the area and the temperature gradient.
Yes. How's it going?
Has anybody gotten an answer yet?
Putting mine in the calculator right now.
Same.
Kiki, what'd you get?
I got 0.67 watts per meter squared degree C.
Per meter squared degree C. Okay, I got the same thing, dog.
So how did it go?
Our group got an answer of 0.67 watts per meter squared degree C.
That answer is correct. Great job. All right, so I'll do a quick run through on how that calculation can be made. So when the problem, it stated that the voltage in the wire was 110 volts. The current was approximately 0.5 amps, which gave a power of 55 watts, which, applying Newton's law of cooling, should equal H times the surface area times Ts minus the surrounding temperature. The surface temperature was given was 150 degrees C. The ambient temperature was, I believe, 20 degrees C. And the area can be obtained assuming only the outer surface and not the ends are conducting heat or emitting heat. We get surface area approximately pi dl, or pi times the diameter, 0.1 meters, times the length, which is 2 meters, which gives us an approximate area of 0.628 square meters, which based on this, to solve for the heat transfer coefficient, it's simply Q divided by the surface area divided by the temperature gradient, or 55 watts divided by the area, 0.628 square meters, divided by the gradient, 150 minus 20, or 130 degrees Celsius. You do this and you get a heat transfer coefficient of 0.67 watts per meter squared Kelvin. All right. Did any groups have trouble or get a little confused on how this problem can be solved? All right. That in mind, let's take a brief look at radiative heat transfer, radiation. So in this is heat transfer through emission of electromagnetic waves. And when we consider heat transfer, we're mainly interested in thermal radiation. And so we can calculate radiated heat transfer and via radiated heat of flux. And we find, just like the other forms of heat transfer, the flux can be denoted by a temperature gradient. However, this temperature is not a linear relationship as we find in conduction or convection, but in radiation, the temperature gradient scales to the power 4. And like the other forms, we have constants of proportionality, where what we can find, I'll make it simpler, is that the first constant of proportionality we consider is designated by a lowercase sigma, which sigma is 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the 4th. And this is known as Stefan Boltzmann's constant. And what we find is that this relation, while valid, only designates what we consider to be the maximum radiation that can be emitted by a body. What we have to consider is how it compares to the actual radiation that is emitted by a body, which is given by the addition of another value of interest, which is known as epsilon, or this is known as the body's emissivity, which describes an object's ability to emit thermal radiation. And emissivity varies between 0 and 1, with an object with perfect or ideal emissivity being given a value of 1. And this is referred to, it's known as a black body, which is also called emitting black body radiation. Which simply states the maximum radiation that can be emitted by an object at a specified temperature. So from this, we can derive one of several expressions. We can describe the heat transfer of radiation by a black body as sigma times the surface area of emission. Now, expanding that gradient out, we find Ts to the fourth minus T infinity to the fourth, or once again, T sub S is our surface temperature. T infinity is our surrounding or ambient temperature. And for every regular system, we have an expression, sigma times epsilon times the surface area, Ts to the fourth minus T infinity to the fourth. And this would definitely be the one I would keep in mind in terms of doing calculations and applying it within systems. Now, one thing I do want to note is for radiation, temperatures must be provided as absolute temperatures, because taking 20 degrees Celsius to the fourth power is very different from taking 293 Kelvin to the fourth power. So with that in mind, let's take one last look at an example dealing with radiation. So let's consider a person standing in a room maintained at 75 degrees Fahrenheit. Determine the rate of heat transfer being emitted by the person via radiation between the person and the surrounding surfaces if the surface area of the person is 15 degrees Fahrenheit and the surface temperature of the person is approximately 92 degrees Fahrenheit. This is our own little matrix human being thermal battery problem. All right, let's take a look. So we got a person standing in a room. Temperature of the person is 92 degrees Fahrenheit. Temperature around the person and on the surfaces of the room is approximately 75 degrees Fahrenheit. The surface area of the person is 15. Did I say 15 square feet?
You did.
All right, and that should be all I need. So based on this, if I want to solve for the temperature, radiation, heat transfer, I have epsilon times sigma times a sub s T(s) to the fourth minus T infinity to the fourth. So the first thing I want to do is probably take those temperatures and areas and make them into SI units. So let's 92F in Celsius. Get about 33.3. And '75 is about 23.9. Which, making that into Kelvin, is 306.3. And 296.9. Converting my 15 square feet to square meters, I get approximately 1.39 square meters. And so the only thing I have left to find, given that Stefman-Boltzmann's constant is still a constant, is the emissivity of the person. So what do we think is the emissivity of a person, a human? What do you guys think? I guess I could go jump on my list, see who's here. All right. The next lucky winner is Bria Thompson.
Yes.
What do you think?
Okay.
We can play the Price is Right. See who can get closest without going over.
Is the emissivity of the person?
Yeah, what do you think? But it's a number between 0 and 1. How good do you think humans are at emitting thermal radiation?
I'm gonna say possibly like, I'm feeling 0.6 or like 0.7.
All right, so I'm gonna go with your first answer.
Okay.
So Bria said 0.6. All right, let's see who can go with her as well. All right, Carl, you got a number for me between 0 and 1.
I'm gonna go with 0.45.
0.45. See, I was hoping you would go 0.61 to just kind of beat her out. Okay, you got to use those Price is Right rules. The actual answer for people on average is 0.95 to 0.98. So we're actually really good at emitting thermal radiation. So for this problem, we're going to use 0.95. So you guys were close, but at the same time, not close at all. But, you know, I give you credit for participation. I appreciate it. So assuming an emissivity of this person of 0.95, we can solve for the radiative heat transfer of the person just standing around in the room not doing anything. As 0.95 times 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the fourth. times the surface temperature, which we had, which is about 306.3 Kelvin, to the 4th power minus 296.9 Kelvin to the 4th power. And if we do this calculation, we find that we get a value of approximately 834 watts.
You forgot the surface area term.
You're right. Fail. Minus 2. See, that's what happens when I don't check units. So the kelvins go away, the meter squared go away, and I'm left with watts. So we still get the same answer because I've already done the problem ahead of time. And we get a final value of approximately 834 watts. So any questions on radiative heat transfer? So this person's like super emits radiation, so we can just be like. All right, that's all I have today for you guys. So any last minute questions? If not, thank you all for attending class. As always, if you have questions, I will jump into office hours here in a little bit. But if you can't make it, feel free to drop me an email.
Thank you, Dr. Lopez.
All right. Take care, guys. Have a great rest of your day.
You too.